the next application of integrals is talking about distributed loads on beams. And we talked about these with regards to derivatives. So you can go back and look again at what we were talking about there. And we changed the variable slightly. But so let's say we have a simply supported beam. So remember, that's a beam that just has the supports on both ends. In this case, it has a length of L. We're keeping it generic here. Capital L, the length. And we've got some sort of load function that's on there. I think we used Q for this before. This time we're going to use W for it, for weight. But it's distributed across there, and it's not necessarily a uniform force. It's a force that changes depending on how far we are down the beam, depending on what it is. And so one thing we know is that we can change this into be a static equivalent load, which means what is this? That having this distributed load across here is the same as if we put one force on the beam at this central point. And so that's what we want to try to find out with this problem is if we know what this function is, can we figure out what the value of that force is and where is it going to be located? So let's see that example. So one thing we need to know is what are the equations that we can use to solve that. And so what they tell us from physics or statics, or depending on how far down the line it's going to be, probably you won't see it until statics, is that to get the force, we just integrate from 0 to L the force function across that space. So across the entire beam, we integrate that function, and we'll get kind of the total force being applied here. Makes sense? And then to figure out where that is, we're going to take our distance times that force, integrate that, and then divide it by that total force to kind of get what is the average x value. We've seen that sort of thing before. So now we'll see an example. So in this example problem, they've given us that the weight function, W of x, is W0 over L times x. So what does that look like? Well, it looks like a linear function that goes up as we go across, and when we get all the way out here to the end, when x is equal to L, well then it's just going to end up being W0. So it's when it starts at 0 and goes up to W0, and we see the force increases as we go along. And we want to figure out what is the total force being applied here and where does that work out. So let's use our equation. So first we're going to figure out what the load is, because we know we need it in the denominator anyway. We might as well solve it first. So remember, it's the integral from 0 to L of Wx dx. We'll plug in our function, W0L divided times x, which was our function right here. Then we'll get the antiderivative. Nice and simple. Since we only have one term, raise the power to 2, divide by the new power, which is 2. We get that. Plug in our limits that we're looking between. We plug in our values. L squared with the coefficient up front. Again, when you plug in 0, we get 0. Very common thing to happen when you're integrating polynomials. So that goes away. We simplify that and get that the total load, the equivalent load is the length times our W0, which doesn't want to give us a term for that, but it's our coefficient there, divided by 2. And remember, this is a force, so it's in newtons. It's a good idea to keep up with the units of things. It'll help things make sense later. Our next part is we have to figure out where that force is being applied. And so we can use this function, which says the equivalent location is the integral from 0 to L of x times our weight force, integrated over x, divided by what our total load is. So again, we'll plug in the values from our example. So a couple ways to deal with this. One is I could do like we did when we were finding centroid and split this apart and just work with the numerator for a minute. Since I've already found R, I'm going to go ahead and just plug it, leave it sitting out there, and use the fact that we know what that coefficient is. So I plugged in the value of R already. We've got this function that we're trying to integrate in the numerator. Let's simplify that a little bit. If I do that, taking this from the denominator and moving it up, so it becomes 2 divided by that when I flip it over, I can pull this coefficient out front and get W naught over L, and then all I'm left with inside is just the x squared term, integrated from 0 to L. So by simplifying, I can say, those will cancel, it's actually 2 over L squared, the integral 0 to L of x squared dx, get the antiderivative, which is just x cubed over 3. We're evaluating from 0 to L. Plug those in. Again, when I plug in L cubed, I get L cubed. When I plug in L, I get L cubed over 3. Plug in 0, I get 0. Simplify that answer. So L squares, 2 of those cancel out. I get L left on top, 2/3. So I get that the place where it's located is 2/3 of the way down the beam. So if I wanted to redraw that, what it essentially looks like is this. So that's distributed load of having that went like this can be described as a single force of W0 over L divided by 2 applied 2/3 down the length of the beam. And notice, if I didn't mention it before, that this is a length, and so it's going to have units of meters. Which again makes sense if I know that the only variable left in here is L, which is a length, which would be in meters. Same thing up here when I did R. W0 is some amount of mass, of weight, so it's that weight times the length. Sorry. But yeah. Whatever that W0 is times N has to get me a force, which is in newtons. And so that is our distributed beam example. The main things were that we can rewrite, if we have a dynamic load that changes as we go down the beam, we can get a static equivalent of that by using this function to get the total force and this function to get the location of where it is down the beam.